Hi everyone. This is our last session of hands-on machine learning. So today I'm just going to share my PowerPoint. Everyone can see my screen, right?
Yep.
Okay. So today, just I need to notify you. Instead of the previous syllables of the last session, I was going to introduce convolutional neural network, which is a deep learning model. But I thought that maybe it's better to use with some things simpler of that one. But I mean, both of them, if you learn this one, it's really easy to convert it to the convolutional one. I mean, at the end of the session, I will tell the difference between convolutional neural network and just a straight or fully connected neural net. So just a brief introduction about what a neural net is. The neural network is an interesting branch of machine learning. I mean, previously in the previous sessions, we have learned about machine learning techniques. I mean, the way that you can give some examples to the computer, and the computer in two methods. I mean, supervised or unsupervised way can do something like prediction, classification, regression, fraud detection. I mean, all the training was based upon seeing many examples and then finding some common features in your data set or among your examples. So the neural net actually is a new branch of machine learning. So it is inspired by the complex functionality of human brain, which process information in parallel using the order of 100 billion link neurons. As you might probably know, I mean, the main function of our body, the way that we are thinking, making decisions, uh, anything that we are doing in our body is based on some neurons in our brain, which are, I mean, connected to each other. And just transmission of some signals do all this process. I mean, all this mathematical process. Actually, I mean, when you're seeing at an object, it's like that our eye is a detector collecting some signals and then feed it to our neurons. I mean, there are different parts in the brain. One part, for example, is responsible for the visuality function of our brain. One is for smelling. I mean, all those things are just based on some signals. So human inspired by this one. And I guess 20 years ago, the guy that I introduced in the first session, Yeshua, who is working in Montreal now, he was the one who first introduced neural networks. So on the right side of my slide, you can see a neural network actually. So I should define some basic definition. We will have an input layer. It means that, let's start with this one. It is that your data set will be converted to a feature vector. Feature vector, it was something that in the first, or I guess second session, I described about that. It means all the parameters that your data set depends on them. So at the first layer, which is called input layer, you will feed all your features here. And these features, by some weights, by some numbers, I mean the blue lines or blue arrows here, which you can see, which connected the first layer or input layer to the second layer. Let me pick my pen here. So this is called first layer of your model. This is called second layer. This is called third layer, fourth layer, and the output layer. So all these layers are connected through some numbers, which people call them weights. So, and as you can see, when you feed your neural net with the feature vector, I mean, here, what it goes here, I mean, the first layer is the feature vector. What a feature vector is, I would provide you one simple example. Just imagine that you have an image which consists of 28 pixels. So by multiplying 28 by 28, you end up finding a number 554, if I'm not wrong. I mean, you would find something in the order of 500 numbers. It means that every single pixel in one image, just imagine that it's an image. Every single picture in this image means one feature. So for training a neural net, you will give any single pixel here to any nodes here. I mean, these circles is called nodes. You will give the feature to the nodes. Then by some weights, which weights are defined here, which they are some numbers. The nodes multiple by some weights and then fit into the second layer. And then, I mean, again, same process, then feeding to the third layer, fourth layer, and finally to an output layer. So, and in every single layer, the neural net is designed in a way that extract features of the input feature vector. It means that, for example, if we are going to do, let's say, image classification. So the first layer, maybe just see some big feature of your images. For example, it can see the vertical line of your image. And the second layer might see the horizontal lines. And the third one might see the curve. So then at the end, you would end up finding some, I mean, a smaller node, which gives you the feature of input picture. But after solving a problem, this would become more clear. So here again, I mean, it's just in the big layout. So we can see in the input layer, your pixels going here. I mean, I'm telling pixels because I'm going to use an example, which is just an image. These pixels could be like as a signal. You can imagine that your input is a signal. And as you know, in DSP or digital signal processing, every signal consists of some numbers. I mean, we are collecting different numbers here to just make this signal. So the input of a deep neural net could be also a signal, could be also a voice, could be pixels or many different values. And the weight that I was talking are this one. I mean, and this formula might look familiar to you. I mean, this is look like the linear regression. So it means that, for example, this one is W1, the second one is W2, and to here WN. It depends on number of input features you are feeding to your neural net. So there is only one difference, which we are using a function. I mean, in every circle here, or every node, we are applying a function which is called activation function. The symbol of activation function is sigma, look like this one. For example, one of the most common activation function here, this means this name is sigmoid function. So if you plot this one, it would have a shape look like this. So I'm sorry, it would have the shape, some things, yeah, look like this one. So it means that for values greater than a threshold, you would have one constant number here, and for values less than the threshold, which are defined here as a threshold, let's say this threshold could be 0.5. For the values below 0.5, you would get something close to 0. And just imagine that if the argument of this function, I mean, this argument of the sigmoid function or activation function, be a small number, then it means that, for example, this node will be eliminated. I mean, it can get the value of 0. So what this means that, for example, the feature that is coming from the first pixel has no important information. So how we can train a neural net? I mean, in a very, very simple explanation. We send the input data set to our neural net. As you can see, the input P, which include connections, which calls weight between neurons, and then you would have an output, which is here, is the output. In the first iteration, we are sending the input feature vector, and then after doing different calculation, the first layer, second layer, third layer, the number of layers could be even up to 1 million. Then you would have an output. Then, in the supervised way, we compare the output to the target. I mean, target is something that we are looking for it. For example, I'm going to do classification. I mean, finding difference between a cat or dog picture. So I know the target. For example, in my first example, I know I'm feeding the neural net with the cat picture. So, and at the output, I mean, because I'm training in a supervised way, I know that, I mean, I should expect to get a cat label. I mean, prediction has to be a cat. So then, I mean, it do the comparison. The comparison here is like loss function, which we calculated. Could be mini-score error, could be cross entropy for classification. Today, we are going to use different cost function. And then by just using that derivative, which I explained in the previous sessions, I mean, of optimization, we can adjust the weights. For example, using mini-score error and do all those derivatives, we can adjust or changing the weights. I mean, the weights which I showed you here. I mean, with the blue line, I mean, the weights here. This method is called backpropagation because, I mean, you start taking derivative from the last layer till to the first layer. It means that you are taking a derivative of the last layer respect to the weight of the last layer, and again do this up to the first layer. So this is called, that's why it is called backpropagation. So now what we are going to do, we are going to do classification between numbers between 0, 1, 2, 3, 4, 5, 8, and 9. So we will have a data set. You have a question?
Yeah, just one small question.
Sure.
What is the difference between, I mean, why do you sometimes use back propagation instead of the normal forward propagation training?
Oh, and forward propagation, let me make this one clear. What forward propagation means? Forward propagation means that you are just feeding your neural net with some numbers, with your pixel. This is called forward propagation. But when we are saying back propagation consists of derivative. It means that you are taking derivative respect to the weights and then equals it to the 0 and then find the, I mean, base value of the weights. I mean, this is the difference between forward propagation and backward propagation. Backward propagation has to do with the derivative and optimization problem, and forward propagation has to do with just feeding a neural net. That's the difference between them.
Okay, so we don't get any weight when you say forward out.
No, for forward, no, you don't get any weights. In the backward, you do. Now, let's imagine that. I mean, let me find a more clear picture. Let's imagine this one. Instead of having 3 hidden layers, I mean, here I do have 3 hidden layers. Yes, just forget about this one. Let's assume that I have 1 input and I have 1 output. What this one reminds you, I mean, to me, this reminds me of linear regression. I have some numbers here and I have Y value. I mean, I have X value here and I have Y value here. And X are connected to the Y's through some weights. I mean, here, I mean, as a linear regression, you saw that W was equal to, Y was equal to W transpose multiplied by X. So this is actually a neural net with just one layer. But when we are going to do some complicated case, we are adding different layers. So, I mean, just by omitting these 3 hidden layers, you can see this is something exactly as linear regression. And for solving linear regression, we were looking for find the weights. I mean, which weights? The weight that give us the best fit to our linear regression.
So just one small question. For the neural network, we always use this backpropagation method, or?
As far as I know, for this type of models, yes, we always use backpropagation. But I also know, I mean, there are some other methods, like, for example, a graph neural network, or other different types, which I'm not aware of them, so I cannot put a comment. But I mean, the most common way of training a neural net is backpropagation.
Thank you.
So today we are going to use a data set that consists 60,000 images. of numbers from 0, 1 to 9. So we are going to train a 3-layer model for doing this recognition. So now if you open your Google Colab, we can start that one.
The link is in the chat box if anybody hasn't opened it yet.
So I will wait for a few minutes to everyone open the link.
Just till guys open
Sure.
it. Just one more question for the neural network. How many hidden layers usually? I mean, people use it. Before, I think if it would put too much, it would become deep learning. No, if you put like 100.
It's a good question. Any neural net with more than one hidden layer is called deep learning. So a neural net with two layers is called deep learning. Yeah, it's the difference between machine learning and deep. It is called shallow model or deep learning model. So anything more than 2 layers is called deep learning. And about the second part of your question, you told that how many layers do we need? So based on my knowledge, if you add many layers, it doesn't change your result. It just, ends up doing more computation.
Okay.
It doesn't hurt if you have more.
So,
but if you have, for example, a million layers, so the training time would be maybe, I don't know, 10 times, 100 times more than that.
Yeah.
And also that there are some, even, one interesting topic of machine learning, which is now a hot topic in research. People, the number of layer, the number of layer is also one feature which needs to be optimized. So even there exist some methods, people are developing methods to finding the best number of layer, because just training is not a problem. You can train a model, I don't know, for 2 months or a year. So, but usually or always people looking for optimized, they want to spend less and get more. So it means that you can use less electricity, so you can train your model in a less time. So this is also a hot topic, that optimizing the number of layers is called hyperparameter. So the number of layer is actually a hyperparameter, which means that it also needs to be adjusted. It was a good question. Thank you.
Okay. I think now we can continue.
Yeah, sure. Let me add one more comment. Even there exist some models that the goal of those models is to finding, we train those models to finding the best hyperparameter for the other models. But that one is really behind my knowledge. I'm really interested to learn about that, maybe in future. But it is also a hot topic. Finding the hyperparameter of another model by using artificial intelligence, by using another model. So now let's back to our.
Thank you. Yeah.
No worries. You can see my screen now.
Yeah.
Okay. So this data set is a handwritten digit, recognition. We are going to use PyTorch. So let me just explain you about the PyTorch. Now you can see also my page, right?
Yes. Yeah.
Okay. In the previous section, when we were going to optimize our model, for example, in the linear regression, in the PCA, in the support vector machine, or no, we did PCA and k-means clustering. So mostly we used, we did coding. We did it by hand. We tried to write down the derivative and then implement the code. But these days, things became so easy. There are platforms like PyTorch and also TensorFlow these two platforms, TensorFlow and PyTorch, are the most common platform that people using for training their neural net. PyTorch was designed by Facebook and is free to use. So, and TensorFlow, I guess it's designed with Microsoft, and this one is also free. So it means that instead of writing 1,000 lines of code, you need to just use the, prepared packages of PyTorch or TensorFlow. I'm familiar with the PyTorch, and PyTorch is more like Pythonic language. The syntaxes, the commands in Python look like more to the Python. That's why I prefer to using this one. And the good thing about PyTorch is that it also has a library that you can use, GPU, graphical processing unit, because using a GPU alone without using some pre-written library is not something easy. You need to code many things. You need to write many line of code for using the GPU, the graphical card on your computer. But the PyTorch, something like PyTorch or TensorFlow, provided all these features. These days designing a model is not really hard. In the practical example we are going to see, you can see with just single line of code, I can optimize or take all the derivatives of the 3-layer neural network, as quickly as in 1.5 minutes. So let's start. So this is our data set. This is called MNIST data set, which consists of 60,000 images of hand written digit, which each images has size 28 to 38 pixels. It consists of 10 different classes ranging from 0 to 9. So now we are dealing with classification problem. It means that we are going to train our model with 50,000 of the data set and keep 10,000 of the data set as a test data set. So we're going to use 50,000 as trained data set and 10,000 as a test data set. As if you recall, test data set means that during a training, the computer would not be able to see the test one, because the purpose of machine learning was making a model in order to predict the data set that has never seen by the model before. So it's not just like a linear regression. So like as usual, we need to import the libraries. Now we need to import the Torch library, Torch Vision. NumPy and PD is familiar with you. We used these two in the previous two sessions. Matplotlib, we already used this one. Torch .nn as NN. This is a neural net library. Torch Vision Transform, and also Torch Functional as F. You will be familiar. Whenever you start working with this, you can familiar with this one. And the best way of learning this, I would recommend going to the PyTorch website, and you can see here, get started. You can find huge examples here. A really perfect explanation. Also, you can use PyTorch from here in this website, which I will send the links also. You can see all the people that are involved in machine learning training the models. It's like Stack Overflow. Write down their questions here. Many people try to answer their questions. It's like communicating between machine learning engineers. And I can say 80% of my thesis has been done here by helping these people. So it's a really good link to use. So maybe I will copy and paste at the end of the session. So let's back to
this PyTorch, this stuff is already built in the Google Colab, right? So we don't need to install anything.
Actually, Google Colab is an online platform for running many languages like C++, Python, or PyTorch. It's a bigger platform. You can import everything there. It's not written in the Google Colab. We are importing them, as you can see.
Oh, okay.
We are importing the Torch or PyTorch, or all the libraries. This is one of the benefits of using Python, because You can import many libraries in just one platform. Google Colab is something like Jupyter Notebook or something like Spider. So this is called IDE. Integrated development environment. So Google Colab, Jupyter Notebook, Spider, PyCharm, anything that you can imagine. I mean, these are called integrated development environment. It means that you can use your language of program of language in those environments.
Thank you.
Did I answer your question?
Yeah.
Okay. So first, let's import the libraries here. So this step is done by just seeing at the green tick on the left side. And then we need to define number of layers and number of inputs. So input size is 784, which means because we had 28 to 28 pixel images. So by multiplying these two, we would know that input size equals to 784. And the hidden layer number one consists of 200 nodes. I mean, what am I going to do? I'm going to decrease the size of my features. It means that in the first layer, I do have 784 nodes. In the second layer, I would have 200 nodes. In the third one, I would have 150. In the fourth one, I would have 100. And in the hidden layer, I would have 80. And the last layer, I would have 10 nodes. What does this mean? This means that by starting from 784 features, which is number of the pixels, right? I make a vertical vector of an image, which I mean gives you a vector of 784. But as you know, most of the pixels has no valuable information. For example, for let's see, for this one, for number 7, just imagine that you have, or I have a better picture here. Just imagine here, number 3 here. Most of the pixels you can see it's just black pixel. It means that for classification, there is no difference between this black here and this black here. That's why I'm using a neural net model that's shrinking the number of features from 784 features. In the second layer, I just keep 200 of them. In the third one, 150. In the fourth one, 100. In the fifth one, 80. And at the last 10. So it means that for classification, I would need just 10 features. 10 features distinguishes between, for example, number 1 to number 9, number 0 to number 2.
And you put the output is just 10 because we have just 10 digits, right? Or we could have put more.
This one was just by chance. I can change this one to the 11. Yeah. It's just it's a coincidence. That's all.
Okay.
So it could be anything. Oh no, sorry, you're right. Yeah. The 10 because we are going to say, you know what this one gives you? This the output layer gives you from 0 to 10, right? For example, imagine my output has to predict number 1. So I can say that if I have a vector at the output which has the value of 0, 1, 0, 0, 0, 0, 0, this means that this vector belongs to number 1. Yeah, you were right. Sorry.
Okay. So
that's why it's 10.
Okay, so if you had like higher, more than 10 class, if you had like 12 class, the output should be at least 12, right?
Yeah, then it would be 12.
We could have put more number of this output. We could have put.
Yeah, exactly.
Okay, thank you.
Because we are doing classification at the end, it's like different bases. We are going to find different. I guess Ayman also found the same question. Okay. So thank you for correcting me.
Okay.
Yeah, 10 because we are dealing with 10 classes. So Now we are going to use a super powerful feature of the PyTorch. Just imagine that if you want to code, I don't know how much you are familiar in coding with Python or even in MATLAB. If you're going to make some list, it's not something easy. You need to write down many lines of code. But now I'm using the Torch Vision library. So the training data set, which means that the data set is going to be used for training the model. I just used a simple line of code, Torch Vision, that data set, that MNIST. I mean, MNIST actually included in the Torch Vision. So I mean, it's already there. The content, the first argument gives you the directory, train equals to true because we are going to use as a train, transforms, doing the normalization. As you may remember in the first session, I told that for training model, we need to engineer our features. One of the most important engineering is converting the numbers to 0 to 1, having the less divergence because of computational problems. So usually what people do, people transform their data between -1 to 1 or between 0 to 1. I mean, depends on the application. But here I can see, I mean, this is between -1 to 1. That's why, I mean, in the transform in this line, we can see we define the transform already. Transform equals to transform dot compose, I mean, to tensor and then normalize between 0 to 5. So, and what this to tensor means in the PyTorch, we are dealing with tensors. I mean, in the NumPy, we were dealing with list or dictionary. Now it's a different name. It is called tensor. And what tensor means? I mean, this tensor is different from the mathematical definition of tensors in physics. I mean, if we have any student in physics, I mean, this one is different. I mean, it's just the same name. So, if you are familiar with the MATLAB, in MATLAB is based on matrix computation. I mean, the power of MATLAB is just doing computation based on multiplication of matrices. I mean, working with the matrices. Here, the power of PyTorch is using tensor. I mean, it's a predefined calculation method that PyTorch has it. I mean, it's open source. You can also go and find out how the tensor is defined. But I mean, for our purposes, it's not important to get deep through. So here I'm just loading.
One more thing, the batch size is also.
Batch size, oh, okay.
Yeah.
As I told you, I mean, here we do have 60,000 images, right? When we are using a batch size, it means that we are dividing these 60,000 in a smaller group. I mean, in the gradient descent session, I told you there are different ways of feeding the images or data to the model. One way is that you feed all your data set in the model, I mean, instantaneously. It means that all 60,000 images, or here, I mean, the training data set would be 50,000 images. One way is just feeding 50,000 examples at once to the model, right? So it's one way of training. But people also using a method which is called batch. I mean, batch means grouping your data. So I'm dividing that 50,000 examples in groups of 100, which means that I would have 500 groups. I mean, using this method, increasing the speed of calculation. This is why, I mean, this is called batch feeding or something like that. I'm dividing the number of training data set to subgroup, I mean, to smaller group. Then I start training with those smaller group over many iterations. And my batch size is now 100. So I had 50,000. So divided by 100 gives me 500. Yeah. So this means that I would have 500 groups that going to train my model.
Thank you.
No worries. So the last argument is download, which is true because we need to download it from a server. Well, the transfer is not defined. So why? Because we didn't run this. So let's run this one first. So then we are going to here. Okay, so we downloaded from here. So now we have all our training data set saved to this one. So we need to also have our test data set. So let's download that one. Again, same, the first argument is the path of the data. Here, I set the train false because I'm not going to use this data set as a training. Transform equals to transfer, which means that I'm normalizing the value of the pixels between 0 to 1, and download equals to true. So now let's see the shape of the train data set and test data set. So you can see the number of data points was 60,000. This gives the location, which is not important. We did a standardization. I mean, we normalize it to having the mean value of 0.5, and we convert it to the tensors. And here, I mean, this one was for training data set. Here for test data set. Test data set has a number of 10,000 examples. Again, we did it the same things, convert to the tensor and normalize it in order to have the mean value of 0.5. What now we need to do? One important thing when we are training a deep learning or neural net is that you need to shuffle your data. What it means? It means that we need to mix them randomly. I mean, if you, for example, start training your model by just all the examples that equals to 1, and train your example in the second iteration by all the examples with the class number 2, then the accuracy of your model would decrease. That's why we need to shuffle our data. It means that we need to randomize our data. So we are using another toolbox of PyCharm, which is data loader. What data loader is doing? Data loader takes the data set, which you can see here, data set equals to train data set. The batch size equals to 256. The reason that I selected 256 is that because the computer RAM can do the calculations when your numbers is in power of n. So 2 to the power of n. 2 to the power of n. This is also true when you are doing fast Fourier transform. So if your vector is in the, I mean, the size of your vector is 2 to the power of n, then your computation would be much faster than, I mean, if I select my batch size to be 100, then the speed of my calculation would be much less than 256. So this one refers to the memory. So memory, I mean, is more adaptable when you select the vectors with the size of 2 to the power of n. This is the reason I select 256. I mean, this could be also be 500 to 12, or let's say 128. And shuffle through, it means that, I mean, it randomized the data. I mean, it kind of mixed the data in order, I mean, in order to just pick the samples by chance. I mean, and also the machine learning was based on a statistic, and the statistic would become true when you are using, when you are sampling from your data set randomly. I mean, not with the bias. So let's run this one. So, and here we are going to see the shapes. So our sample consists of 100. I mean, every single group that is going to be used as a training data set contains 125 examples. This number 1 refers to the number of channel. What channel means? I mean, when you take an image, you are working with RGB, red, green, blue. But here we are using grayscale images. So our channel is just 1. 2828 is the height and width of the image, and 128 is the number of output we are expecting, because I mean we are feeding the neural net with 128 examples. So we are going to classify 128 examples. So let's plot the figures. I mean, for just I mean, these single pixels, I mean, with the group of 128 examples are going to fit in our model. So then we need to define or design our neural net. I mean, here I'm using fully connected layer. What it means that every single node or every single input feature is connected to the every single node of the second layer. I mean, we don't, everything is connected, because I mean, in some other type of machine learning models, you may have something like some misconnection, or maybe you're using convolutional neural net. So in convolutional neural net, basically just a few pixels are connected to the next layer. I mean, because of some reasons, which is not important now, but here we are going to use fully connected, and fully connected means that every single neuron is connected to every single neuron in the second layer. And every single neurons in the second layer is connected to every single neurons in the third layer, and so on. So I'm going to define the class in Python. How we define the class, and maybe start with the class and name of our class. And in the parentheses, we are going to inherit some features from NN module. What NN module is? I mean, NN module is here. I mean, I just imported that. If you can see here from the PyTorch library, I imported the NN module. So what this means that I'm defining a class with this name, MNIST, which includes the library of NN. So then my model or my class depends on these 6 parameters: self, input size, I mean this initial input, which was 754. Hidden layer number 1, hidden layer number 2, hidden layer number 3, hidden size, the last one, and the output. Then here, I mean, self.f connected one, I'm using linear regression in every layer. So you will fit with the input and the hidden size number 1. I mean, for simplicity, let me show you this one. I guess by showing the PowerPoint, it become more familiar for you. So yeah, here it was. What I'm going to define now, I'm just going to tell my computer that the first layer, I mean here this one is 728, this one is 200, this one is 150, this one is 80, and this one is 10. So it's just schematic. So, and I know that the number of input here and number of output here, I mean, it has to be matched. I mean, the output of this one has to be matched the input of this one. I mean, for this case, I mean, these are just, I mean, equal 5, 5, which is not true. But I mean, the real case, which I'm going to deal with that. Let me show you another example. So I can find you the actual one. Yeah, this is the model that we are dealing with, this one. So the input layer is 728. The second one is 200, and third one would be 150. I mean, we are decreasing the number of nodes. So here, what you basically can see is this one. I mean, the input size, which is 754, hidden size one, which is 200. I mean, from big features, I'm going to have small features. Let's just define this class. And here, just again, see the shape of training. I mean, we have this on before. And I put the name on my model. I call it as the MNIST model. So here is just defining the name of the model. And here I'm defining the loss function or optimization method. My loss function is cross entropy. Cross entropy is something like minuscule error, but cross entropy is using for classification. Minuscule error was using for regression. So here again, you can see I'm using the PyTorch library. I mean, I do not need to define the minuscule error. I mean, previously in the last 2 sessions, for defining minuscule error, I wrote all the codes about how to calculate minuscule error. But here instead, I just did this one, nn.cross-entropy. For example, in the previous session, you could also do this one, right? Loss equals to nn dot mean square error. I mean, instead of those those four of lines in the previous session, I could just use this simple one. I mean, but here I need to use cross entropy because I'm doing classification. So let's define the cross entropy and also optimizer. I mean, as I explained in the previous session, one of the optimization method was gradient descent. Here, Adam algorithm is based on gradient descent, but in a more sophisticated way. So again, I mean, the gradient descent, you remember defining gradient descent was equal to writing 4 or 5 lines of code. But here with just single line of code, I defined an optimization method. I mean, I defined the gradient descent. I mean, even a way complicated gradient descent than the simple version by just one line of code. So let's define this one. And now I'm going to train this model on a GPU. One great feature of using Google Colab is this one. You need to come here, runtime, and then change your runtime. So here it's already GPU. You can see it means that the Google providing you a free GPU, a free graphical processing unit. I mean, you do not need to have GPU on your computer. So let's start the training. So here, what basically training is doing, in every single iteration, I'm sending my input images to the model, then compare it. I mean, here is the output, is just sending images, which images is a data set. Sending to the model, and then in the loss function, I'm comparing between output and the label, I mean the actual one. And in these two steps, I'm basically just applying the gradient descent. I mean, these 3 lines basically just applies gradient descent. And the last 2 lines, printing the error of the model over each iteration. So let's see the training. So in the first iteration, my error was 0.4. Second iteration, error was 0.3. Third one was 0.4. I mean, slightly jumped up. Again, 0.3, 0.1. I mean, it's decreasing actually. One interesting thing, you can see that now the values is fluctuating between 0.2 and 0.1. So what hyperparameter is, even now, I mean, it's increasing, which is not supposed to. So tuning, now we are going to deal with hyperparameters. Sometimes you need to change the batch size. So for example, I changed my batch size from 256 to 128. So now just, I mean, at the end, you can see my error is decreasing. It's going to 0.7, right? But I remember just a few hours ago, which I was writing the codes, my error was less than this because my batch size was 256. So sometimes when you are training a model, you need to play with the parameters of your model, changing the batch size, changing the learning rate. Learning rate here is 10 to the minus 2. I can change it to 10 to the minus 1 or 10 to the minus 4. So, I mean, these are all called hyperparameters. So now for just, I mean, showing you how it affects your model, I'm coming here and change the batch size here to be 256. 56 and here 256. I change basically one hyperparameter. Again, I need to run all these things. My model, this one. But you can see that there is error. Why? Because we defined our weights. So now we need to start over, start from the beginning. we need to come here, runtime, and restart runtime. It means that all the weights will be clear, and we have to start from the beginning. So first run this one, define this one, download our data set, download the test data set, defining the model. Again, defining the model. So you can see, you don't see the error anymore. Defining the loss function and start training.
You could do the same thing on the without the GPU also, yeah? With
Yeah, it's on GPU now. Yeah.
Okay. How much it would take? I mean, normally with the same system, if we don't use the
with the CPU.
Yeah, like for three times longer, or
for this simple example, I did even. I mean, I wrote the codes here. I mean, below here is based on CPU. So the difference was not much, but maybe it was 1 minute or something. But I mean, because this one was pretty simple model. But when we are dealing with more complicated model, the difference would be really huge. I mean, I remember for my own data set, using CPU, it took me like 5 hours to training my model. But when I switched to GPU, it just took 10 minutes. So you can see huge difference. I mean, I don't have a exact number. I cannot say by a factor of what it is changing. But I would tell that, I mean, invention of GPU was, I mean, critical point of machine learning, because without GPU, you can never train, let's say, 1,000-layer model based on CPU. I mean, it never happens. Maybe you need to spend years. But when people started to using GPU, I mean, the training time dramatically decreased. I can say by a factor of 10,000 maybe. I mean, it's really effective. And now even you can see, I mean, we end up having faster. I mean, I didn't record the time, but this one was faster. I'm not going to run the CPU. I mean, maybe at home for the practice, you can do this one. I already wrote the code here. I mean, and if you just compare the codes from here to here, the only thing is that I use .coda. I mean, .coda is running everything on GPU. I mean, one of the also interesting feature of PyTorch is just this one. By just writing .coda, you can convert everything to the GPU. So you don't need to do something a lot. And here I'm going to check the accuracy of model. So I trained on GPU, so check the accuracy of model. What basically it does, I had a test training data set, which consists of 10,000 examples. Here, I'm going to see how a pre-trained model can predict this test example. So, and then print accuracy. So let's create a line of code here and just print accuracy. So my accuracy was 96.875%. So it means that, let's say 96%. So it means that in every 100 example, the 96 of them can be predicted by the model correctly. So my error is just 4% in this model. Question?
Yeah. I don't see any question over there, but okay. How much is it? I mean, I'm not familiar. How much is the typical accuracy for this kind of?
This number is really great.
Okay.
Yeah, 96 is really good number. Again, the accuracy, I mean, the value of accuracy depends on your model, on your application. I mean, for medical purposes, so as much as higher accuracy you get, for sure you would have better result. For financial things, again, same. I mean, always higher accuracy is better. But for this specific example, 96 is actually a good number. So you can also try convolutional neural net. What convolutional neural net is doing? I mean, the convolutional was my first purpose to explain, but then I realized that in 1 hour and a half is not really enough to explain convolutional operation. But convolutional neural net is basically just convolution operator. If you remember what convolution was doing, convolution, when you're applying convolution between two functions, it gives you the similarity between two. So by getting that meaning and applying that to the machine learning, you can again speed up both training time and also the accuracy of your model, mostly on images. I mean, also on signals, but mostly people use convolutional neural net for image classification or image segmentation. So maybe you can look it up later and find a good explanation for that. I'm also happy to share the codes about convolutional neural net, then you can just run and see the difference. But again, I mean, as I told you before, let me just answer one question here. It's based on just a test data set.
The question is that is the accuracy based on just the test data or the whole number of used data trained plus test?
Here, this number, which 96, is accuracy for test data, right? But here, this error, I mean, 0.08, this is the error based on training data set. So, but usually what is important, applying a model on the data set which has not been seen by the model is important. If you get better accuracy on the test data set, that would be much better than if you have better accuracy on your training data set. I mean, in the first session, I told you one of the critical problem of machine learning is overfitting or underfitting. So you should basically make the difference between test data set accuracy and train data set accuracy equal. So this makes it kind of challenging, because if you train your model over a lot of time and also many layers, you might end up finding overfitting model, which means that your model is working perfectly for your training data set, but your model has poor performance on your test data set, which is not good, because the whole purpose of machine learning is that machine has to be able to work with something that have not seen before. But for this one, it's just this 96% refers to test data set.
Okay, I think I don't see any. I heard also about these other methods that like cross validation. So they divide the data to few different sections and they train some parts and then test different parts of the data set just to make sure and make an average at the end.
Yeah, cross validation is actually like checking your model on the test data set, but during training. So I didn't apply this here, but during training, you can also do kind of testing. You can divide, I mean, we do have, I mean, in reality, I mean, in super practical things, we have 3 types of data set. One of them is training data set, validation data set, and test data set. Training data set and validation data set are using during the training. You train your model and you check your model based on validation data set. If you see that the validation error is decreasing, but your training error is increasing, then you need to stop the training. If you see that the training error is decreasing, but the validation error is increasing, you need to stop your training. But here I didn't include them for just making things simpler. So the validation and training using during the training. But the test is just when you fix your weight. I mean, whenever you fix all the weights, I mean, whenever you train your model completely, then you apply it on the test data set.
Okay, so it doesn't depend on if it's regression or its classification. In both of them, we can apply this cross validation,
actually,
right?
You should apply. Yeah.
Okay.
Yeah. It's kind of, I mean, strongly recommended to apply validation data set. I mean, all this because of not overfitting. And also sometimes you need to use some sophisticated method like drop connection. What drop connection means? It means that during training, some of the nodes in my neural net would be disconnected. I mean, it's kind of trying to make your neural net to not be biased on your training data set. I mean, just randomly turn off some of the nodes. So, I mean, but there is a really complicated mathematics behind this. But I mean, mostly mathematicians are involved in this. I mean, developing algorithm, and you cannot believe that. I mean, mean set data set. I mean, what we just did this year is the basis of many publications in machine learning. People to try to develop some algorithm, mathematical algorithm, and then apply this data set to see the performance. I mean, but what is important in performance is your accuracy is important. The speed of the convergence. I mean, training your model is important. All these parameters are important. I mean, if you can make a model as simple as possible, train it faster, having higher accuracy, this means that your algorithm is working better. But most of the people in the real world, for example, I have many friends working in the financial institute, working in the Bell company. I mean, different institutes. I mean, they feel they're working with machine learning or data science. They just know how, like as me, I just know how to implement models. But behind the models, I have no idea. I mean, I have some intuition what the mathematics behind is, but I mean, I'm not algorithm developer. I mean, the hard thing is for people who are dealing with mathematics. I mean, they are developing the huge part, and maybe, I mean, I'm just picking a number. 90% of people that you are using machine learning model, they just know how to use machine learning model, and how they learn to do that by just using PyTorch from, I don't know, GitHubs, copy paste from different sources. I mean, it's the way of learning, starting things. So it's not something, I mean, I'm not shy about that. I mean, I did all my thesis on that. I can say that all the people answer my questions during my PhD. So I mean, I did it, I published publication and it's working. So I guess for starting, it's also good to use GitHub, to use online sources, even to copy and paste the codes, but then try to understand what is going behind these codes. And I mean, I'm assuming that none of our audience here are machine learning algorithm developer. They are going to use the application of machine learning. So simply you can publish many papers. Like I say, in a month you can publish a paper once you learn how to do that.
Yeah, I mean, here, I mean, the whole workshop was intended for people who are a little bit the beginner side, or or something like maybe intermediate, but not the professional.
Yeah.
Okay, so maybe we could take a small break and then we come back.
Oh, okay. Well, I don't think we need to come back with this all. I don't have nothing to, but I have two comments. One of them, I will share all the codes, all the PowerPoint slides, but I'm pretty sure that you can find much better than mine, I mean, in the web. I will also include all the links that I have used during my PhD to learn about machine learning and Python. Because I mean, in Coursera, you can find a lot of good not free courses, but there is a trick for finding free courses. So I guess this part would be more important, all these 3 sessions. Whenever you are going to apply for Coursera, there is financial aid. Having 2 accounts is important. Make one of your email, I mean, one that you are using, and make one fake email, I mean, something that you are not using. So start the course with your fake email, because once you audit the course, it means that once you accept that I'm going to take this course, but I don't need a scholarship, they don't give you the certificate. But you can start your learning, I mean, with your second email, and then apply for financial aid. So after 2 weeks, you can get the course free. And the courses cost like $100, $200. So I got like 7 of them free. So you can do the same things. I will send you the list of the courses that I started machine learning. So it's a very good resources. I'm sure in 3 sessions, even if you get 5% of what I told here, I mean, it's the best. So
maybe,
but after a few months, yeah,
we
maybe
need to
I can
cut
ask
this
you
part.
questions.
Yeah, no, I think we need to cut this part before uploading to YouTube.
Okay, yeah. So
thank you.
Next thing for students, I mean, next comment. If we have any students here working on optics, image processing, I would be happy to cooperate, because for some reasons I need to have a few papers on machine learning. So I'm offering, like, as I don't know, helping or collaboration. So if anyone has an idea, I'm at INRS. We can start talking about that, doing some project. I'm just expecting to be in some machine learning paper because I need it for some purpose. And also I can find some financial sources, I mean, some industrial sources or whatever. So if anyone's interested, also can contact me. I mean, if we have same path, same interest, then we can do some collaboration. I mean, it's also increasing your research and also giving me my benefits.
Okay, I thought you wanted to show some of this for your thesis, some.
Okay, yeah.
I don't know if you want to do it or no, because
if you are interested, I can show.
Yeah.
Yeah, I have it here. I can just stop sharing and go to my thesis. I mean, this is basically.
I mean, something that was looking like more applied and more like a little bit advanced version, so people also can see, okay, how a little bit more complicated scenario, how it looks like.
Maybe, yeah, it's a good idea.
I mean, not explaining in detail maybe, but just
just quickly in a few minutes.
Yeah, so we can get a feeling about that, how it works.
So what I did during my PhD, I was doing optics, I mean, doing microscopy. So I was dealing with hyperspectral images. What it means that I was recording not only spatial distribution, but also spectral distribution. It means that in every single pixel, I also recorded the spectrum of that pixel. With the optical setup, look like this, which is not important. So my data set was a 3D data set. It means that I had X, Y, and Z. X and Y represents the spatial distribution of the sample, and Z represents the temporal or spectral information about my sample. So I used a convolutional autoencoder. I mean, one of the purposes of using machine learning for me was for denoising images. So as you can see here on the left side, GT, it means ground truth. This image was taken when the laser power was really high. So you can see the contrast is good, the signal to noise is good, the picture looks pretty good. And the input, the second image, the B, was recorded when I turned down the laser power by a factor of 10. So as you can see, I lost the contrast. And also I added some noise by just decreasing the laser power. And in the third and fourth one, I applied deep learning model. So as you can see, the contrast of image increased. I mean, just compare the input one and this one, SH rate and UH rate. You can see the contrast improve. I mean, this has been done by using deep learning. So one of the application is for denoising. You can denoise your images or your signals by applying machine learning method. And the model that I use, it names autoencoder denoising. So what it looks like, and also here you can see the left column represents the input images, which I mean, it was when the laser power was low. It means that I had a lot of noise, and also the contrast of my image was not good. In the two middle column, I applied machine learning on the first column, I mean on the input noisy one, and in the last column, you can see the GT ground truth, which means that when the laser power was high, I mean, the purpose of machine learning was building this noisy one, the column A, look like to the column D. So which you can see in B and C, I mean, we did this. We use machine learning and kind of reconstruct the image even when our laser power was low. But why you need to turn down your laser power? For example, when you are dealing with some biological sample, you do not want to cook your sample. I mean, if you overheat your sample, you might, I don't know, burn a cell or something. Or if you're dealing with explosive, you do not need to trigger that sample. So that's why you need to decrease your laser power. Or maybe you have a weak detector, or maybe your signal to noise is low. And as an example of a signal, you can see this one at the left side has a really low signal to noise. And then after applying the machine learning model, I could increase the signal to noise to this one and this one. And you can see this is comparable to the fourth one, which fourth one is when the laser power was high. I can say the factor was 6. By factor of 6, I changed the laser power. I mean, so you can see basically by applying deep learning model, I could reconstruct a signal that look like here. I mean, these three. This one is the best one, which was recorded when we had high laser power. These two is just based on the model, output of the model. And this one is when the laser power was low. So, and the other purpose of autoencoder I used was for classification. For example, here I use a mineral sample, which consists of quartz, spodumene, feldspar, background, and some dead pixels. So it means that in my images, I had 5 classes. So then by applying machine learning, I could not only denoise the signal, but also classify. For example, in this part of my image, the red refers to the quartz. The orange refers to the feldspar. It's a mineral sample. The blue refers to spodumene, which is a lithium sample. So you can see by applying deep learning, I could not only denoise my signal, but I could do classification. And this was done based on purely unsupervised way. And the model that I use is look like something this, for just your curiosity. I used I use this one. I use this model. I mean, this one, I was going to implement this one in this session, but I mean, it was taking really long time. So I use a convolutional autoencoder. What basically is doing, we are encoding information and then decoding. So as you can see, input layer has more features. Then once you are getting deep through the neural net, the number of features decreasing, and you end up having a layer which is called latent space. Latent space in autoencoder is a space or layer that contains all useful information about your signal. It means that everything you need to reconstruct your signal is here. And here, just for giving you an numerical example, my input size was 65,000 features. I mean, I had a vector, which the length of vector was 65,000. And you cannot believe with just 3 data points, I could reconstruct those 65,000 data points. I mean, I was shrinking the data point size from 65,000 to just 3 points. I mean, this latent space here is just three numbers, 3 points. Then by applying another neural net, with just 3 points, I could reconstruct 65,000 points. So, I mean, this is one of the powerful methods. I mean, this is called encoding and decoding. When you encode something, it means that you are forcing your model to just keep the useful information about your data set, about your signal. I mean, and when you decode something, it means that by just having important feature of that sample, you can reconstruct your whole signal. I mean, from 3 data points here, I reconstruct 65 data points there. So, and because you are shrinking your data to 6 to 3 useful data points, it means that you are getting rid of all the noise. The reason that I could also do denoising is that because I mean, noise is something from not useful information, some randomness. So, and randomness doesn't mean important information, doesn't contain important information. So by applying encoding model, you are getting rid of all those not necessarily information and just ending up having some useful information, which here for my case was just 3 points. So three points could make 65,000 pixels.
Just for curiosity, how many hidden layers you had here? And yeah,
we can count. Every two counts as one. 1, 2, 3, 4, 5, 6, and 7, 8 layers. This one was 8-layer neural net. Yeah.
Okay. And how long? I mean, they took for you the training of this?
Now this tells you the importance of using GPU. With CPU, it takes 5 hours. With GPU, it takes 10 minutes.
Ah, okay.
Big difference.
That's, yeah, it's a really big difference.
Yeah. And one more important thing about hyperparameter I told you. So number of layer, I mean, it took me like maybe 8 months changing how many layers you need, changing, for example, what activation function you need, changing, I don't know, many different parameters like number of layers, which was most important, learning rate, for example, the step size you need to do your iteration. The first time I took the step size of 0.1, it was really big. So that's why I had a great error. So then I changed it to 0.1, 10 to the minus 4, 10 to the minus 3. So this is one hyperparameter. You can change number of your layer. It's the second hyperparameter.
You've done also in your this reduction of the dimensions as well?
Yeah, I did. Yeah, this is called dimension reduction. Yeah. Basically, autoencoder is a way of dimension reduction.
Okay, yeah, that was really nice actually. Yeah, I read your.
Thank you.
Yeah,
you did.
It was very nice. Yeah,
so
I read not all of it, but a little bit.
Sure.
Some part of it, yeah. I mean, I didn't understand most of it actually, but yeah, it was just good to get some like a real application, how it looks like, just to have some feeling when we do. Hopefully, one day we should have some.
Yeah, for sure.
Yeah. Okay, if guys, do you have any questions from this session, or if you have some maybe small short questions from the previous sessions, you can drop it now. And the sessions are recorded. We will share it later on YouTube on our channel, and then we will send you an email when it's up there. And of course, any these information like slides and stuff, and any useful links that we had, data sets, I will get it from Dr. Abdolghader, and then later I will email all the registrants on it. So if you don't have any questions, I will thanks again Dr. Abdolghader for his time for this very useful workshop. Hopefully, all of us learn some stuff. And thank you, everybody.
Sure. Have a good day, guys. Bye-bye.
Bye-bye.